So let's talk about these bottom two. Last time we had to find the vertex. What does AOS stand for? Good. And the y-intercept, and decide whether it was a minimum or a maximum. That's probably the easiest part if you're looking at the graph, is finding out if it's a minimum or maximum. But if you're not looking at the graph, which is what the next section is about, there's ways that you can tell just from the equation whether it's going to be a minimum or a maximum. So that's like for the next section. But for now, let's take a look at this one. So what is the vertex? Yeah, it's right there. That's not positive 1, though. That's negative 1, comma 3. And now the axis of symmetry, x equals negative 1. That's a negative 1, right? That's going through negative 1 on the x-axis. Okay. These two numbers right here will be the same. The x-coordinate of the vertex and the number that you write for your equation for the axis of symmetry will be the same. Okay, the y-intercept seems to be right there. So we're going to write down the ordered pair 0, 2. That's right. And then minimum or maximum? Maximum is correct. And this last one, this very small parabola here, what do we have? So the vertex is 1, 3. Good. And next? AOS is not just 1. It's not just 1. It's an equation. So you have to write the equation. It's x equals 1. Has to be an equation, okay? It's not just a number. And then the y-intercept. Yep, the y-intercept is also an ordered pair, 0, 4. And then finally, max or min? Minimum. And if I wanted to, I could draw in the axis of symmetry right through the vertex. There it is. We're going to be doing that a lot in this chapter. All right, the next thing we're going to learn is called standard form for quadratic functions. This is standard form for quadratic functions. Y equals ax squared plus bx plus c. This should look familiar to you. This ax squared plus bx plus c thing, we looked at that in the last chapter. We were looking at this sort of trinomial when we were factoring using the box method. Remember that? Okay. So that's what we're dealing with. Now, there's some things that are going to be on here that are pretty important. This c right here, we already know what that c is. What is it? It's the y-intercept, right? We're going to be talking about this a right here also, and what it does to the parabolas when you graph them. So we'll get there. So for example, y equals 3x squared, y equals x squared plus 9, y equals x squared minus x minus 2. Those are all quadratic functions that are in standard form. The reason that they're quadratic functions is because of this squared right there. The squared right there. The squared right there. They all have a squared term, which makes them a quadratic function. If that squared term was not there, then you'd have a linear function. It would form a line. But that squared term makes the parabola when you graph it. Notice that the x squared term is coming first in all three of them. The x term, if it's there, is coming second. There wasn't one there. There wasn't one there, but there was one there. And the constant term is coming last. There wasn't one there, but there was one there, and it's last. There was one there, and it's last. Okay? So that's standard form. The simplest quadratic function is y equals x squared. That has no number in front of it. It has no other terms behind it, just y equals x squared. That is the most basic parabola that we can draw. Nothing has been done to it. It's called the parent function. I'm going to write that down because that's a good vocab word. It's not really a vocab word you need to know. The parent function is y equals x squared. In Algebra 2, if you take Algebra 2, we'll talk about parent functions a lot. All right, we're going to graph y equals x squared. We actually already have graphed y equals x squared. It's such a simple function, I'm not even going to make a 3-column table here, but I am going to pick some numbers. -3, -2, -1, 0, 1, 2, 3. Negative 3, I square it and I get 9. Negative 2, I square it and I get 4. Negative 1, I square it and I get 1. 0 squared is 0. 1 squared is 1. 2 squared is 4. 3 squared is 9. So to graph this, negative 3, positive 7, 8, 9. Negative 2, positive 1, 2, 3, 4. Negative 1, positive 1. 0, 0. 1, 1. 2, 4. 3, 9. And it's worth saying again, notice how the symmetry of this parabola kind of falls along this y-axis right here. What I did on one side already showed up again on the other side. Over here, showed up again over here. Over here, showed up again over here. This is going to come into play later on when we start learning some of these shortcuts for working with quadratic functions and parabolas. So draw on your smooth curve. Starting off of the grid at that dot is very convenient to have. Nice smooth around through the vertex and back up on the other side. Arrows at the ends. Your parabola does need to go all the way through the grid that you're given, and you're done. So that's the graph right there. This is the same graph that we just made. Y equals x squared. F of x equals x squared is the function that we're looking at, okay? And here is our parabola. It's the exact same parabola, except now we're looking at Geometer Sketchpad so that we can quickly come up with a bunch of different graphs. So what I want to do is show you what happens as we change the number that is in front of the x squared. What's the number in front of the x squared right now? It's not 0, it's not nothing. If we don't see a number in front of a variable, what is it? There is a number in front of that variable. How many x squareds do we have? We have 1. It's a 1 in front of that x squared, okay? So what I want to do is I'm going to double click on this and bring up my function window so that I can make changes to the x squared. Let's make a 2 in front of that. What happened? Seemed like it got a little skinnier. So let's make it 4 this time. What happened? Got even skinnier. Let's make it an 8. It's getting skinnier every time. So let me make it something ridiculous, like maybe 24. So what can we say as the number in front of x squared is getting larger? The parabola gets skinnier. That's right. So let me go the other way. And by the other way, I don't mean make it negative. We'll talk about that in a minute. The first number that I entered in was 2, right? So let's talk about 1/2. What happened? It got wider, yeah. So let me go back to the original, just to refresh your memory. This is the original, the parent function, just x squared, or 1x squared. Now if I make it 1/2, it gets wider, or fatter, I'll say sometimes. So let me make it something even smaller than that. Instead of 1/2, let's make it 1/4. Let's get another smaller fraction than 1/4, maybe 1/8. These fractions are getting smaller each time, right? Okay. The parabola is getting fatter. Notice that the vertex is still sitting right here at 0, 0. The only thing that's changing is how wide this parabola is. So the number in front of x squared controls how fat or how skinny the parabola is, okay? If the number is bigger than 1, the parabola will become what? Skinnier, smaller, yeah, thinner. If the number is between 0 and 1, a fraction between 0 and 1, what happens to the parabola? It gets fatter than normal, okay? Now let's see what happens when I make that same parabola with a negative sign in front. What do you think might happen? You think upside down? You're exactly right. Good job. Notice that it's still fat, right? It is exactly the same parabola, except now it's upside down. That's the only difference. So the negative sign out front controls if it's upside down, or if you don't see a negative sign out front of that x squared term, it'll be opening up. With the negative sign, it opens down. So if I see a negative sign, without even looking at the graph, if I see a negative sign in front of the x squared term, I already know if it opens up or down, which means I already know if it has a maximum or a minimum value already. Okay? So let me just make sure that we're right here. Let's turn this back into just negative 1 x squared. And there's your normal parabola. It's just that now it's upside down instead of right side up. And then if I make it a negative 4 instead of a negative 1, what will this be? It'll be skinnier but still upside down. And there you go. Okay? So, like I said, I'll keep saying this too. There's a lot of patterns in these equations, and if you can learn those patterns, you can see the graph without even really graphing it. You get to a point where you can picture it in your mind before you even try to graph the thing. And then there's a bunch of shortcuts that we can learn that help us graph this very, very quickly. And that's towards the end of the chapter. We'll get to that point. So now back to the notes. You can use the equation of a parabola to tell you some of its characteristics. Characteristics means the things that you notice about it. For example, in equations that look like y equals some number times x squared, that's exactly what we were just dealing with. If a is positive, then the parabola opens up. If a is negative, then the parabola opens down. That's what we just saw. What happens when a gets larger or smaller? As a is greater than 1. If a is greater than 1, then the parabola gets what? Skinnier. So we're going to write skinnier. I'll write thinner, because sometimes I'll say thinner, sometimes I'll say skinnier. If a is between 0 and 1, so that fraction between 0 and 1, like 1/2, 1/4, 1/8, what happens to the parabola? It gets wider. And I could also say, I probably will say, fatter. So let's see now if we can do this problem without even looking at the graphs. What is the order from widest to narrowest? So let me put narrower. I don't need parentheses. So widest to narrowest of the graphs of the quadratic functions. All it's asking for is widest to narrowest. It's not saying up or down or anything like that. So which one of these is going to be the fattest, the widest? The fattest one is the second one. Okay? What's going on this one? It's skinny and it opens down. This isn't asking for up or down though. It's just saying which one's fattest, right? So which one is the fattest here? This one. F of x equals 1/4 x squared is the widest. Then what? Yeah, because this one is going to be wider than this one. This is going to be super skinny, right? This is the skinniest one of all three, so it's got to go last. This is your standard, just your parent function. Nothing was done to it, so f of x equals x squared is the middle guy. And then finally, f of x equals negative 4x squared is the skinniest one. And that's how you do a problem like that. All you got to do is look at the front number, and it will tell you how wide or how skinny that parabola is. How is the graph of y equals 2x squared plus 3 different from the graph of y equals 2x squared? Well, okay, so let's look at the answer choices. It shifted 3 units up, it shifted 3 units down, it shifted 3 units to the right, it shifted 3 units to the left. Have we talked about shifted at all yet? No. So let's bring Sketchpad back up, and that's my calculator. Let's bring Sketchpad back up and take a look at equations that have maybe had something else done to them. So we've looked at having a number in front. Let's look at what happens if we have a number behind. So here's my original function, and let's put a number behind it. So like maybe x squared, and I'll put a plus 1. Enter. What happened? What went up 1? So the parabola got shifted up 1, right? Actually, where does this parabola cross the y-axis? and that would be called the y-intercept, right? So by putting that plus 1 outside, I changed the y-intercept. I made the y-intercept 1. So let's put a plus 4 on here. What would happen if I put a plus 4? So the vertex is going to be at 0, 4. The y-intercept is at 4. Hit enter, and sure enough, there it is. How could I get a parabola? So this is called shifting up, by the way. From here, I've shifted the parabola up. How could I get this thing to shift down? Like maybe I wanted it at -3. Yeah, subtract. That's right. So I can put, instead of x squared plus 4, if I want that parabola to be shifted down to -3, I can write x squared minus 3. Oops, minus 3. Enter. There you go. That's it. Okay. So I'm shifting up and down when I have something outside, when I have something trailing that x squared term. Okay? So let's go back to the notes then and take a look at these two equations. We have 2x squared plus 3, and we have 2x squared. Where is this one going to be? Where is the vertex here? At 0, 0. Where is the vertex here? So what happened to my original parabola after I added that 3? I shifted 3 units up. That's right. So the answer must be A. Okay, last problem. An acorn drops from a tree branch 20 feet above the ground. Can you picture that happening? Okay. The function that they give you, this equation, it says the function here gives the height of the acorn after t seconds. What is the graph of this quadratic function? At about what time does the acorn hit the ground? So yes, because we know with that negative sign, what happens? The parabola opens down because of that negative sign. With that 16 in front of the t squared, the parabola is now fatter or skinnier? It's actually very skinny with that 16 right there, right? With that plus 20, what happened? Crosses the y-axis at 20. The vertex got shifted up to 20. So since I have a sketch pad sitting right here, let's change this to that equation. So I need a negative 16, and the fact that I'm using x squared is the same as t squared in the problem. It's not a big deal. And then it says plus, what was it, 20? Okay, so hit enter, and we have a very skinny parabola. I'll just scroll up so that we can see. Actually, I'm going to have to zoom out as well. There you go. It's a very skinny parabola. The vertex is at 20, and it's upside down, exactly what you guys told me. So just by looking at the equation, you can already picture what the graph looks like. Now, the question asks, at approximately what time does the acorn hit the ground? Well, let me zoom back in. This is the height right here. It starts at 20 feet up and it falls to the ground. So at approximately what time does it hit the ground? This is my time axis. This would be 1 second. 1.5 here, so maybe 1.1-ish. It just says about what time. So about 1.1. About 1.1 seconds. Or if you were using graphing by hand or something, you might just say about 1 second. Okay? So let's put a sketch in there. We don't have to put in a really good-looking parabola because we don't have a bunch of data points, and that's okay. Let's put a sketch in there of our parabola. We know that the vertex is all the way up at 20. We know that it crosses the x-axis just after 1. So I'll put a 1 and a 2 in there. And then all I got to do is draw on a parabola that kind of does that. So I'll put a dot there. I'll put a dot there. Now, do I need to draw the other side of the parabola? This is time, right? Over here would be negative time. Can I have negative time? No. So I actually don't even need the other side of that parabola. I just need to draw in a parabola-looking shape like that. And that is good enough. So you can do this problem without even really graphing it. Okay? It's kind of cool.